Logarithms and exponential functions. Now, we're used to being able to figure out problems like this. 2 to what power is 8? Well, we know that that's 3. So 2 to the third we know is 8. Or 6 to what power is 36? Well, we know that 6 squared is 36. So 6 to what power is 36? That's 2. But what about a problem like this? 7 to what power is 54? Well, we know that that's not any real nice number because 7 to what power is 54? I have no clue. I could probably try to do some figuring it out by doing some guess and check and getting some close approximations. But there's actually a new mathematical function that you've not been exposed to called a logarithm. Now, we're not talking about musical logs or musical trees. But a logarithm really means 7 to what power is equal to 54. We would write 7 to what power equals 54 as log base 7 of 54. So that's how you would read this, log base 7 of 54. Our base is a subscript, and your base is whatever your exponent's on over here. So a logarithm is really just representing an exponent, and the exponent that you happen to be looking for. So we have the exponential form. You've seen this, something to a power equaling something else. If you go from the exponential form to the logarithmic form, you can use your definition of a logarithm. B is your base. That's what goes over here as a subscript. What was on one side by itself goes after the log. And a, the exponent, is what goes on one side by itself. So a is your exponent, and then a is your exponent here equaling a logarithm. So once again, a logarithm is just an exponent. Now, pretty much whatever's after your log has to be positive. So your base has to be positive, and this part that is at the normal level has to be positive. So keep that in mind. So to go and write this in the exponential form, we take our base, which is b, goes to the other side. What was over there gets hit up as the exponent, so we take our 8 to the other side, hits the 2 up as the exponent, and it equals that 64. Same idea here. We take our base of 16, swing it to the other side, hits the 2 up as the exponent, and then it'll equal the 4. Now, in both of these here, you should know that an 8 squared really is 64, or a 16 to the 1/2. Remember, 1/2 power means square root, is 4. So whether you are looking at it in the logarithmic form like you were given or exponential form, they both mean the exact same thing. Same idea here. We'll take our base of q, swing it to the other side, hits the t up as the exponent, and then it'll be equal to 7. Here we'll take our whole base of x plus 2, swing it to the other side, and it hits the st up as the exponent. So here we want to do the reverse process. We want to go from the exponential form to the logarithmic form. So 27 is your base, because your base is whatever your exponent's on. 1/3 your exponent, so you know since the logarithm's an exponent, that 1/3 will go on the other side by itself. So we'll go log of our base of 27, put the exponent on the other side. What was on the other side by itself goes after your logarithm at normal level. Same idea here. The maroon x is your base, a is your exponent, so it'll go log of your base, put the exponent on the other side, and that 12 would have to go after your log. Here we would go log base 10 of 100 is equal to 2. By the way, a little bit of pre-teaching. As a side note here, we could write this as just log 100 equals 2. Once we get farther going into this stuff, you'll learn that if there's no base written, it's assumed to be base 10. But for right now, write what we have up here. So we'll go log of our base, which is what is in the parentheses. Put our exponent on the other side, and then what was over here goes after your log. So we need to evaluate this. This means 10 to what power is 1,000? And well, you should know that 10 cubed is 1,000, so this whole thing equals 3. So this means 2 to what power is 8? Well, 2 to the third power is 3. So this whole thing here equals 3. So you want to think about it in these terms of these words here. So even on this next one, it means 9 to what power is 3? Well, you should realize that if you take the square root of 9, you get 3, and you should know that the square root of 9, square root's 1/2 power. So log base 9 of 3 is equal to 1/2. Here this means 8 to what power is -5. But 8 to any power is always positive. So there's no way to get this answer. Another way you could think about it is whatever's after your log always has to be positive. And -5 is not, so it does not work. This means 8 to what power is 1? Well, you should remember from earlier that that would be 0, because 0 to anything other than 0 is 1. So if log base 5 of x is equal to log base 5 of 7, if they're equal and it's the same log base on each side, then what's after your logs has to be equal. Same idea works for inequalities. If it's the same log base on each side, whatever's after your logs would have to follow the inequality. So whether you're dealing with exponential functions or logarithmic functions, it follows very similar. So in solving something like this, there's nothing we can do at this point in the log form. So all we have to do is go from the log form and rewrite it in the exponential form. So that takes our base, swings it over, hits this up as the exponent. So we get n raised to the 8th, or n raised to the 8, if I can talk here, 8 raised to the 4/3. So that means we'd have to do the cube root and then take the 4th power. Cube root of 8, you know, is 2, take it to the 4th power, and we get 16. Similar over here, there's nothing we can do, so we have to go ahead and get your variable out from after your log, so we'll put it in the exponential form. Take your base of 27, swing it over, hit the 2/3 up as the exponent. Remember, the denominator of the exponent tells you which root to take, the numerator tells you what power to raise it to. So we take the cube root of 27, we get 3, still got to raise it to that 2nd power, and we get 9. So if you had an inequality with a logarithm only on one side, whatever's on after your log at the normal level, normal size, that inequality has to stay hanging out next to that one. So the x has the big part by it, so when you rewrite it, the x has to have the big part by it. So here we can go from the log form to the exponential form. We can take our base, swing it over, hits the 3 up as the exponent. But since the big part was by the x, we got to leave the big part by the x. And now we just work out the right-hand side and we get this. Same type of thing over here. We take and write it in exponential form, take your base of 3, hit it over as the exponent, and we get this. Now, what the x had the small part hanging out by it, so the small part has to be hanging out by the x. And so we get this. But also remember, whatever's after your log right here has to be positive. So x can't be negative and x cannot be 0, so that means x would also have to be greater than 0. So in other words, we have to be smaller than 9 to get this to work. But because of the definition of a logarithm, we have to be greater than 0. So if you're greater than 0 and smaller than 9, that's one region on your number line, so you could write that as one compound inequality.